Hi, and welcome to today's video on proving triangles congruent. We're going to be looking at the Sss method and the Sas postulate to test for triangle congruence. Included angle is a vocabulary word we'll be talking about later in this lesson, and that's really the only word that should be new to us today. So we have this first postulate, the side, abbreviated SSS congruence, meaning if all three sides of a triangle are congruent to all three sides of another triangle, for instance, AB is congruent to ED, AC is congruent to FD, and BC is congruent to FE, then that means triangle ABC is congruent to triangle DEF. So thinking about this in terms of a flow proof, we are given that QU is congruent to AD, as you see in the diagram. We also know that AU is congruent to DQ, or QD. We want to prove that triangle QUD is congruent to ADU, and we want to use our side theorem, SSS. We know that this side and this side are congruent, this side and this side are congruent. We just need that third side. So what we can say is we know that QU is congruent to AD by the given. We know that the same for QD and AU. And finally, the only thing we need to prove is that that third side is congruent. And we know that DU is congruent to DU based on the reflexive property. So because we were able to prove all three of those things, we can use the SSS postulate to show that triangle QUD is congruent to triangle ADU, and I'll write SSS. And mine's a little messy, so let me just show you a nice version of that proof. You can see it right here. The box is labeled for the reasoning why we went with that. So go ahead and check your progress now. We have AC is congruent with AB, and D is the midpoint of BC. We have a flow proof there. See if you can figure out which is missing in the blank. So in this example, we want to look at the coordinate plane. We have triangle DVW having vertices at -5, -1, -1, -2, and -7, -4. Triangle LPM has vertices at 1, -5, 2, -1, and 4, -7. We want to graph both those triangles on the same coordinate plane, and then use our graph to make a conjecture as to whether the triangles are congruent and explain our reasoning. Then we'll write a logical argument using coordinate geometry to support the conjecture we made. So first, the graphing part is pretty simple. You just put the points on the coordinate plane here, draw them all out as they were given to you. And then for part B, we want to use that graph to make a conjecture. So let's go back to the graph. And that's kind of up to you. To me, they do look they look about congruent, because I can see this almost three rectangles filling the middle part, with these four squares looking about even with this part, and then these two squares looking about even with this part. So I'm going to make a conjecture for part B that they are congruent, now I just want to be able to prove that conjecture. So in order to prove it with our side theorem, we have to prove that all three sides on this triangle have corresponding sides on this triangle. So as you can see in the graph, we can use the distance formula. D equals the difference in my x values squared plus the difference in my y values squared, the square root of that. If we're thinking WD is congruent to LM, let's find the length of W, which would negative 1, 2, 3, 4, 5, 6, 7. What we can actually do, instead of getting into the distance from, let's just look at the actual distance between the x values. You can see that they're 2 apart. So let's just put 2 in and see that the y values of D and W are 1, 2, 3 apart. Square that. We get 2 squared plus 3 squared, which is 4 plus 9, or 13. So WD has a length of 13. LM, let's take a look at that. We take its difference in x values, which is 1, 2, 3 squared, plus its difference in y values, which is 2 squared. And as you can see, we get the same. Let's look at dV and compare it to LP. dV, with the y values, there's a difference. So we'll square that. We get 16 plus, which is 17. With LP, we look at that segment, we get difference in x's is 1, and the difference in y's is 1, 2, 3, 4. So we get 1 squared plus 4 squared, which is 1 plus 16, or 17. So as we can see, we already see that 2 sides are congruent. Let's just prove that third one. WV has got a difference of 1, 2, 3, 4, 5, 6 for x, of 1, 2 for y. Squared plus 2 squared is 3, 6, 4, or 40. The difference in x of 1, 2 squared plus the difference in y of 1, 2, 3, 4, 5 squared. And 36 plus 4 is going to give us 40. So because the 3 sides have congruent parts on the other triangle, we can prove by our postulate SSS that they are congruent. So go ahead and see if you are able to use that postulate to show that a triangle ABC is congruent with triangle DEF. Now let's take a look at our second postulate, the side angle side congruence. Basically, we don't necessarily need to know all 3 sides are congruent. If we have 2 sides, such as AB and BC, being congruent to ED and EF respectively, if we know the angle between those sides, that's enough to prove that the triangles are congruent. So basically it's called side angle side, or side angle side. You can prove that those. So in this one, we have the wings of a moth forming 2 triangles, FEG and HIG. We want to write a 2-column proof to prove that those 2 triangles are congruent if we know that G is the midpoint of EI and FH. So, and we also know that EI is congruent to FH. So we know that this segment is congruent to this line segment here. By definition of midpoint, we can say are congruent. These segments are congruent. So the proof is that these angles, because of angle head and side angle side, we can show that these angles are congruent. And what theorem proves that these angles are indeed congruent? We know that that's the vertical angle theorem. So let's form. Again, we're given that G is the midpoint of those two line segments, and we know that EI is congruent to FH. So we used our midpoint theorem to say that FG is congruent to HG and EG is congruent to IG. I drew those hash marks on the triangles. And then we just used vertical angle theorem. Once we had all that information, we could use side angle side to prove that those two triangles are indeed congruent. Fill in the blank of this proof. Which one is going to allow you to say that this middle line BG is congruent to BG? So now we want to write a paragraph proof to prove that angle Q is congruent to angle S. And we know that RQ and TS is are parallel, and RQ is congruent to TS. So because these two are two parallel lines, you should see that, for instance, these are congruent angles here and here, because you have alternate interior angles between the lines. So we also should know that RT is equal to itself because of the reflexive property. So notice right here we've got wrong angles, by the way. I had angles RT and STR are congruent, because what that's going to allow us to say is we have side angle side, because we know RQ and ST are congruent, so side angle side. By the reflexive property, we know that RT is the same on both triangles. So just to see that written out as a paragraph, because RQ and TS are alternate interior angles, or because they're parallel, alternate interior angles. So those alternate interior angles we pointed out have the same measure. So RQ and TS and RT and RT are congruent by the reflexive property. This was the reflexive property. Therefore, triangles QRT and triangle STR are congruent because of side angle side. And because congruent parts of congruent triangles are equal, we can say that finally triangle Q is congruent to triangle S. So try this one out. See if you can figure out that missing property that can tell us that segment DC is congruent to BC. And that's going to conclude our lesson on those two very important postulates in proving triangles are congruent, SSS and SAS. Have a good day, and as always, if you have any questions, feel free to let me know.